Hey everyone, I'm back. I'm back with my sparkle pen. I'm super excited. So I hope you had a chance to look at the synthesis history video. That was just more fun than anything, but I just wanted to make sure you had a file with a bunch of links, so you should have that PDF on your Blackboard, and then along with the little spiel that I gave. So half of our class now and half of our tests leading forward will have synthesis. So test 3, test 4, test 5, and the final. Half your test will be mechanisms, half will be synthesis, a little bit of roadmaps, and a little bit of fill in the blanks. So I want to take this video to just give the basics of synthesis. What is it? How do we do it? What are the arrows? What does it look like? What is the vocab? And kind of show you my process for synthesis. Of course, your process could be different. Synthesis is my favorite because it's kind of like playing chess. So we always start our unit with the mechanism. The mechanism tells you how that reaction works, and it gives you the rules to that reaction. It gives you stereochemistry, how it happens, where it happens, the order it happens. Our mechanism really gives us the rules. So it's kind of like in chess, you just learn the rules to the pieces. But then synthesis is where you actually get to play chess. It is all about strategy. And pretty soon there is more than one right answer. It's awesome. So as long as you're following the rules, I like to make my test challenging, but I do not break the rules on our reactions. So I like to make my synthesis challenging, but I will not break the rules for our reactions. So let's start with some vocab. We learned in that video the importance of synthesis. And typically what happens with synthesis is that you actually start with a goal in mind. You know, if you're working for industry or research or academia or anything, you're going to have some type of goal in mind. That always happens. So if you're in a pharmaceutical company, you know your drug target. That is your goal. Okay, it would be awesome if you could just plug that into a 3D printer and make it. That would be perfect, but unfortunately that's not how it works. So typically you need to start with something that is cheaper and easier to get your hands on. And for us in OChem 1, that will be an alkane. Alkanes come to us from the petroleum industry. They are cheap and easy to get their hands on, and in fact, they are one of the largest feedstocks on the planet for organic synthesis. So we just think of them as gassing up our car, but in fact, that's where an awful lot of our materials actually start, somewhere in the petroleum industry. Alkanes is no exception. That's where we get them, and you can usually get your hands on alkanes nice and reasonably priced. So a synthesis is typical to actually write it backwards. So we're going to start with some sort of alkane, but our goal is actually this product. And that's the whole point of synthesis. You've got to start somewhere, something you can get your hands on, and then end up with your goal at the end. So we typically use what's called a retrosynthetic arrow. That is this funny looking arrow right there. So if you're just drawing out your ideas and you are working backwards, that is what retrosynthesis is. You are deciding, okay, I know my goal. How am I going to get there? I know I can start with this because I can order it and it's affordable. But what I really want is to start here and end here. So how do we make that happen? So you'll sometimes see synthesis problems with this retro arrow. It is okay for me if you draw your synthesis backwards and do a retro arrow. You can also show your synthesis forward once you have your ideas in place. So let me show you my process for working backwards. So if you recall, this is a sparkle pen moment. If you recall in class, how do we make organic hard? We put a bunch of crap on it. We draw it funny, and then guess what the third one is? We work backwards. All of that was leading up to synthesis. We're going to work backwards. So we know that our starting material is going to be an alkane, and we know that our goal is to make this substituted compound. So if we are going to start here, in theory, and end here, Now our job is to put the steps in there. So I really like to work backwards. My brain works backwards when I'm doing a lot of synthesis because you have to have in mind your goal. So what I do is I start here. I start with the product, and the first thing I do is look for a functional group. Typically, your functional groups you will put last. They interact with other things. Our functional groups are the steps we just learned how to make. Functional groups can start doing other chemistry. So you tend to put those on second, like this functional group right here. If we can identify our functional groups, of course we have an alkane. That's what we're going to start with. But holy crap, what is this right here? This is a nitrile. Now this is where your flowchart comes in handy. Your nitrile, if you look back through your notes and you look at your flowchart, you will notice that we indeed have made nitriles. Yes, we have made them. And we have made them in only one way. So if you just list everything on your cheat sheet and you just have one massive list of reactions by the end of this semester, you're totally screwed. That's way too many reactions to worry about, think about, memorize. What you need to do is find ways of making your life easier. And out of that whole list, if you only know how to make a nitrile in one way, then that's where you start. Because now we know, okay, how do we make a nitrile? So now our complicated problem turns into, okay, wait for it. Let's go and picture that our problem now is, okay, how do we make this functional group? And let's picture one step backwards. Let's do one step backwards. And picture this like a fill in the blank, okay? So if we're gonna make a nitrile, where does that nitrile come from? Where have we seen nitriles? They've been in only one type of reaction. If we're moving one step backwards in the unit we just did, let's look at our product. Look at your product. This is why we start synthesis on this test. Is your product the product of a substitution or an elimination? And how do you know? Well, if you have an elimination, don't you need a double bond? You don't have one. You have a substitution. Isn't that awesome? So now you know above your arrow, in here, in order to make this compound, I need either an SN2 or an SN1. Now your flowchart is helpful for this. How do we distinguish if we need an SN2 or an SN1? Well, we look at our electrophile. What kind is it? Is this primary, secondary, tertiary? This, where are we adding what? Let's look. This is your nitrile. So you are substituting here. And if you think about where that's coming from, that will be coming from a secondary carbon. So can we do an SN2 on a secondary carbon? Sure. Can we do an SN1 on a secondary carbon? Sure. So how do you decide between the two of them? Where have you seen nitrile before? Have you seen it in an SN1 or an SN2? You have seen it in an SN2. The only way that you can actually attach that nitrile is by using sodium cyanide. Oh, isn't that exciting? And then now if you've decided, okay, I've just decided SN2, I've decided cyanide, what's our missing piece then? You look at your perfect conditions for an SN2. What kind of solvent do we need? We need something, let's take a second, let's erase here. We need something polar and aprotic. So you could use anything that's on your list. In the past, we've used DMF, we've used acetonitrile, we've used DMSO. Any of those work. And then now, what is the missing piece? We have our product, we know our nucleophile, we have our solvent. What is the part that we're missing? We're missing the electrophile. So what does that have to be? Well, where does your substitution happen? It happens on your leaving group. Could I just start with an alkane here? Heck no. Why? Because you don't have a bond that's going to break. You don't have an electrophile. Alkanes are not electrophiles. You have to have your alkyl halide. So we just went one step backwards. Awesome. So if you were in the lab, you could now take this starting material right here, take your electrophile, stir it up with some sodium cyanide and some DMF, and you would make that product. Except this now is not quite done, because we do not have an alkane yet. We have an alkyl halide. Aha! How do we make that? So remember, our goal is to start from an alkane and end with that. So can you make this alkyl halide from that alkane? Absolutely. How do we do that? There is only one way: radical halogenation. So at the end of this whole process, this is your thought process. This you write on scratch paper. What would your actual answer or synthesis look like? It would look like the forward reaction. Let's write it in here between these two, and your forward reaction would be in 2 steps. So your answer could simply be bromine and light, sodium cyanide, DMF. Done. There is your answer. Oh, I feel like we need a sparkle pen for that, and we need rainbow. So if this were a test question, you don't need to draw the mechanism. You don't need to show me your whole thought process. What you need to end up with is just this. This is your synthesis. You could start from your alkane, do a radical halogenation, and then an SN2. Awesome. So you have a bunch of synthesis in your homework and a bunch of synthesis on your practice test. So definitely try some of that before we do another one of these. I'm going to pick another example that's a little bit trickier and post it in another video. So take a minute to kind of think about this and apply some of this to your homework before you watch the next video, which will be a little bit more complicated substrate. And then I'm going to work my way through a practice test and kind of show you what I would do if I were taking